In this section, we're going to be discussing L'Hopital's rule. So let's get started. So consider the function f of x equals the natural logarithm of x over x minus 1. Since f is undefined when x equals 1, we may wonder what the limit is as x approaches 1 for f of x. For polynomials, it was sometimes possible to use algebra to simplify the limit, but that is not possible in this example. So if the limit as x goes to a of f of x over g of x, where both f of x and g of x approach 0 as x approaches a, then the limit may or may not exist and is called an indeterminate form of type 0 over 0. Similarly, if the limit as x goes to a of f of x divided by g of x, where both f of x go to either positive or negative infinity, then as x goes to a, then the limit again may or may not exist and is called an indeterminate form of type 0 over 0. So note that the limit can also be as x goes to infinity, that is, a can be infinity. These two situations can be handled using L'Hopital's rule. So suppose that f and g are differentiable on an open interval that contains x equals a, and that the limit as x goes to a of f of x over g of x is type 0 over 0 or infinity over infinity, then the limit as x goes to a of f of x divided by g of x is equal to the limit as x goes to a of f prime of x divided by g prime of x. So note, if we have an indeterminate form of type 0 over 0 or infinity over infinity, this says that if we take the limit of the numerator and denominator separately, it preserves the value of the limit. Also note that we do not use the quotient rule when we do this. It's just f prime over g prime. All right, let's take a look at example number 1 from our handout. So this first example can be solved using purely algebraic methods like we did at the beginning of the class. So let's go ahead and analyze that method. So by algebra, we can factor the numerator as the difference of squares, and we get the limit as x approaches 2 of x minus 2 times x plus 2 all over x minus 2. We then reduce that out, and we get the limit as x approaches 2 of x plus 2, and then by the evaluation theorem, we just plug in 2 for x, and 2 plus 2 gives us 4. We can also note that this is type 0 over 0, because if I plug 2 in for x, I get 2 squared minus 4, which is 0, and in the denominator, 2 minus 2 is 0. So since it's type 0 over 0, by L'Hopital's rule, it says that the limit as x goes to 2 of x squared minus 4 all over x minus 2 is the same as the limit as x goes to 2 of the derivative of each of these. So the derivative of x squared minus 4 is 2x, and the derivative of x minus 2 is 1. This is now a continuous function, so by the evaluation theorem, I get 2 times 2 over 1, which equals 4. And we'll note that we got exactly the same thing whether we did it via algebra or by doing it via L'Hopital's rule. All right, so let's take a look at a couple of other examples. So if we start with the one we looked at the very beginning, we want to evaluate this limit. First thing we'll notice is that there is no algebra that we can do that will allow us to simplify the natural logarithm of x, or the natural logarithm of x over x minus 1. So if we do test it, if we test x equals 1 that gives us the natural logarithm of 1 over 1 minus 1. Well, the natural logarithm of 1 is equal to 0, and 1 minus 1 is 0, so this is type 0 over 0. So then, by L'Hopital's rule, we get that the limit as x goes to 1 of the natural logarithm of x all over x minus 1 is equal to the derivative of each of these. So the limit as x goes to 1, and the derivative of the natural log of x is 1 over x, over the derivative of x minus 1 is 1. So we simplify that up a bit, and we get the limit as x goes to 1 of 1 over x. Well, now by the evaluation theorem, we get 1 over 1, which is 1. Let's take a look at our next example. So we have the limit as x goes to infinity of x squared over e to the x. So this time, as x goes to infinity, infinity times infinity gives us infinity squared, which is still infinity, and e to the infinity is infinity, so we have type infinity over infinity. So then, by L'Hopital's rule, once again, we get that the limit as x goes to infinity of x squared over e to the x is equal to the limit as x goes to infinity of, and the derivative of x squared is 2x, over the derivative of e to the x is e to the x. And if we test this again, we get 2 times infinity is still infinity, and e to the infinity is still infinity. So we get type infinity over infinity. So then, by L'Hopital's rule again, we now take the derivative one more time. So we have the limit as x goes to infinity, and the derivative of 2x is just 2, and then the derivative of e to the x is still e to the x. So now this time, as x goes to infinity, we have a constant divided by infinity, and a constant divided by infinity gives us 0. So in this example, we had to use L'Hopital's rule more than once. And in fact, we can use it again and again and again and again. There is something that's worth observing in this, is our numerator this time was a degree 2 polynomial x squared. So a degree 2 polynomial, after we take 2 derivatives, it's going to be a constant. But no matter how many times I differentiate e to the x, I will always get back e to the x. So in terms of using L'Hopital's rule, if we look at it this way, the exponential will always beat a polynomial because the derivative of e to the x is always e to the x, but the degree of the polynomial will go down by 1 every single time. All right, let's take a look at our next one. It's a U-try for you guys. So we have the limit as x goes to 0 of cosine x minus 1 all over x. So we want to evaluate this limit, and if we check its type, if I put in 0 for x, cosine of 0 is 1, and 1 minus 1 is 0, so I get 0 in the top, and 0 squared in the bottom, in the denominator, is 0. So this is type 0 over 0. So then, by L'Hopital's rule, we take the derivative, and we have the limit as x goes to 0. The derivative of cosine is negative sine. Derivative of 1 is 0. And the derivative of x squared is 2x. So once again, we try to take our limit, and if we put in x equals 0, the sign of 0 is 0. So once again, this is type 0, and 2 times 0 is 0. So then, by L'Hopital's rule, again, we get the limit as x goes to 0, and the derivative of sine is cosine, and the derivative of 2x is 2. So then, we finally plug in x equals 0, and the cosine of 0 is 1, so we get negative 1, and the denominator is constant. So by the evaluation theorem, we get negative 1/2. All right. So just as a recap, we had in these examples, we were talking about indeterminate forms of the type 0 over 0 or infinity over infinity. So now we want to introduce a new type of indeterminate form. So our next indeterminate form involves products. And there are two ways that this can happen. So we have an indeterminate form of type 0 times infinity if the following happens. So if the limit as x goes to a of f of x times g of x, where f of x goes to 0 and g goes to plus or minus infinity as x goes to a, then the limit may or may not exist and is called an indeterminate form of type 0 times infinity. So when taking limits, we can't assume that 0 times infinity is equal to 0. This limit can be any number. It can be 0, it might be infinity, or it could be the number 12. And the only way to find out is to actually evaluate the limit. So this indeterminate form is algebraically equivalent to type 0 over 0 or infinity over infinity. So if we look at our first product right here, where we have f of x divided by g of x, it's worth noting that g of x can be rewritten as 1 divided by 1 divided by g of x. Because if you have a fraction divided by a fraction, this is equivalent to the fraction 1 over 1 times the reciprocal of the bottom. But the reciprocal of 1 divided by g is g over 1, which gives us back g of x. So that's exactly what we had happening here, is that g of x here can be rewritten as 1 over g of x. So we're using this fraction rule backwards. We can do a similar thing for f, but the reason we want to do this is now if we can rewrite this as type 0 over 0 or type infinity over infinity, we can then apply L'Hopital's rule to this new rewritten function. We do have to be a little bit careful since there are two ways that we can do this. Sometimes one method of rewriting it, that is writing it as f over 1 over g, will make the problem really, really easy. But writing it the other way, as g divided by 1 over f, will make it very, very hard, or vice versa. Unfortunately, there's no way to know in advance other than to look for some patterns. So let's go ahead and investigate a little bit. So let's take a look at our first example. So we have the limit as x goes to 0 from the right of x times the natural logarithm of x. So if we put in 0, that's going to give us x is 0, and the natural logarithm of 0 is infinity. So this guy is going to be of type 0 times infinity. So as we were talking about above, there are two different ways that we can rewrite this. So the first way is we can take the limit as x approaches 0 from the right of x over 1 over the natural logarithm of x. The other way that we could write this is the limit as x approaches 0 from the right of the natural logarithm of x all over 1 over x. All right, so let's start working in the left-hand column. So now, as x goes to 0 from the right, in the top, we get 0. And the natural logarithm of 0 is infinity, but a constant over infinity gives us 0. So this is type 0 over 0. So now, by L'Hopital's rule, we need to take some derivatives. Okay. So in the numerator, the derivative of x is going to be 1 over, and then in the denominator, we need to take the derivative of 1 over the natural logarithm of x. So then our f is 1, and our g is ln x. So then f prime is 0, and g prime is 1 over x. And the quotient rule is g times f prime. So we're going to have ln x times 0 minus fg prime, 1 times 1 over x, all divided by g squared, which is the natural logarithm of x squared. So then we simplify that up a bit, and we get the limit as x approaches 0 from the right of 1 over x divided by the natural logarithm of x squared. So we've got a fraction divided by a fraction divided by a fraction. So we have 3 compound fractions. So the first one is going to be 1 over x times the natural logarithm of x squared. Then we have another fraction divided by a fraction, so we get the limit as x approaches 0 from the right, taking the reciprocal again. All right, this is over 1, so this is 1 over the natural logarithm of x squared. Then we take the reciprocal once again, and we get the limit as x approaches 0 from the right of x times the natural logarithm of x squared. We're looking at this, and what was the original problem we started with? X times the natural logarithm of x. And what do we have now? X times the natural logarithm of x squared. It's worth noting this is more complicated than the original. So let's try the other one. So if you're doing a problem like what we were just doing, and after doing it, you realize it's getting more complicated instead of less complicated, we do have an alternate choice. So let's go ahead and apply L'Hopital's rule to this. And we need to take the derivative of 1 over x, which is the same as x to the negative 1. So then we take our derivative, and we have the limit as x approaches 0 from the right, and the derivative of ln x is 1 over x, and the derivative of x to the negative 1 is negative x to the negative 2. So we get negative x to the negative 2, which is negative 1 over x squared. So once again, we have a fraction divided by a fraction this time. So we multiply by the reciprocal, and we have 1 over x times negative x squared over 1. So this simplifies down to the limit as x goes to 0 from the right of negative x. Well then, by the evaluation theorem, that is equal to the number 0. And that would be our solution. Okay, it's now your turn. Let's have you guys go ahead and do your U-try. So once again, if x is going to infinity, we have x is infinity and e to the negative infinity is 0. So this is type 0 times infinity. So if we rewrite this by moving the e into the denominator, we get x over e to the x. So now, as x goes to infinity, this is infinity and this is infinity. So this is type infinity over infinity. So we can apply L'Hopital's rule. But based on what we saw earlier, we have a polynomial versus an exponential. Well, who's going to win, the polynomial or the exponential? Well, it should be the exponential, but let's verify. So by L'Hopital's rule, we get the limit as x goes to infinity of 1 over e to the x. And so then we have a constant over infinity, which will give us 0. Our next type of indeterminate form involves, instead of products, when we have exponents. So for limits of the form limit as x goes to a of f of x raised to the g of x, where we have the following: the limit as x goes to a of f of x is 0, and the limit as x goes to a of g of x is 0. This is type 0 to the 0. We have where a, or f of x goes to positive or negative infinity, and g of x goes to 0. We have type infinity to the 0. And our last one, type C, is we have f of x goes to 1 and g of x goes to infinity, and we have type 1 raised to the infinity. By using logarithmic properties, this is equivalent to the following. So let's go ahead and correct this. So let's get rid of that. And then we have this limit. So if we take the natural logarithm of both sides, we have the natural logarithm of L is equal to the limit as x goes to a of the natural logarithm of f of x raised to the g of x. So then by my log properties, I can bring the g of x down in front. So then this is equal to the limit as x approaches a of g of x times the natural logarithm of f of x. So in each of these cases, if we check now, we're going to get a type of 0 times infinity. So let's just verify a. So the natural logarithm of 0 is infinity, and if the limit of f of x equals 0 as x goes to a, the natural logarithm of 0 is infinity, and if g of x is 0, we're going to have type 0 times infinity. And if you verify the other ones, you'll see that all of them reduce to the type of 0 times infinity. So let's go ahead and take a look at our next example. So we have the limit as n goes to infinity of 1 plus 1 over n raised to the nth power. So this is going to be type 1 to the infinity, because on the inside 1 over n goes to 0. So the inside goes to 1, and the n on the outside goes to infinity. So then, if we take the natural logarithm of both sides, we get the natural logarithm of L is equal to n times the natural logarithm of 1 plus 1 over n, and the n just came down in front. So yeah, let's go ahead and do this. What we have going on here. So then, as n goes to infinity now, we're going to have infinity times 0. So now, this is of type infinity times 0, which means that we can rewrite it as type 0 over 0 like we did in the previous set of examples. Well, based on what we observed above, when we had this logarithm times a polynomial, which one did we choose to move into the denominator? Well, when we tried to move the logarithm into the denominator, we ended up with something that was more complicated. So, based on what we saw above, let's move the n into the denominator. So we're going to get the limit as n goes to infinity of the natural logarithm of 1 plus 1 over n divided by 1 over n. So finally, this is going to be type 0 over 0. So using L'Hopital's rule, we take the derivative of the numerator, and the derivative of the natural logarithm is going to be the following. So remember that d dx of the natural logarithm of f of x is f prime of x divided by f of x. So we're going to get 1 over 1 plus n, that's our f of x, and then the derivative of 1 plus 1 over n is going to be negative 1 over n squared. And then the derivative of 1 over n is also going to be negative 1 over n squared. So then, multiplying by the reciprocal, we have the limit as n goes to infinity of negative 1 over n squared divided by 1 plus 1 over n times negative n squared over 1. So then, reducing, we get the limit as n goes to infinity, and in the numerator, negative n squared times negative 1 over n squared, they reduce out and we just get 1. And then in the denominator, 1 times 1 plus 1 over n is just 1 over n. So now as n goes to infinity, this guy goes to 0, and we get 1 over 1, which is 1. But this, if we remember correctly, isn't the limit. This is the natural logarithm of the limit L. So this gives us the equation ln of L is equal to 1. So if we solve for L, we get L is equal to e to the first power, which is just e. So the value of that limit is Euler's number e. So that's the end. You'll notice the U try that was here is actually the same problem that we just did.